There we go.
Or I could just get out of the way. So welcome, everybody. I think we're in good shape and set to go. 3 cheers for Marina, who's got to come to every seminar for the rest of the year. I will be teaching 310 winter semester next door. So just if you could plan your calendar around it. Few reminders between informs and break. We do not have class the next 2 weeks, so we will see you all in 3 weeks. Also a shout out to Stephanie, who is more on top of grading than anybody I've ever seen and making everything else work. So, and she's not here for, where'd she go? Oh, there she is. So a big shout out to Stephanie. And finally, let's get poor Erkin started. So Erkin Otles is a medical scientist training program fellow, which as far as I know is a fancy way of saying MD, Ph.D. With 3 years of medical school training under his belt and doing his PhD here in the IOE department. His research lies at the intersection of computer science, industrial engineering, medicine, centered on creating machine learning and artificial intelligence tools for patients, physicians, and health systems. His dissertation work focuses on the development, implementation, and prospective usage of dynamic health outcome prediction models as used in early warning systems. He is co-advised by Dr. Brian Denton, who is also chair of IOE, and I think on the screen, hi Brian, and Dr. Jenna Weens, computer science and engineering, as well as precision health, and I don't know if she's on the screen or not, but if she is, hi Jenna. He has a master's degree of industrial engineering from the University of Wisconsin, and we won't talk about football, but I noticed he's wearing a Michigan mask. And after completion of his MD PhD training, he plans on pursuing medical residency training in emergency medicine. Welcome and thank you for being here.
Thank you, Amy. Thanks for being here. Thanks for braving one day afternoon to come here to talk in person. So you guys got the background. I'm Erkin, co-advised by Jenna Weens in computer science and Brian Denton in IOE. And my contact info is there. It'll be at the end as well. And if you guys want to talk about this fancy program at some point, I'm very happy to talk about MD PhD stuff, either during this talk or later. So I want this talk to be super, super interactive. So I have a lot of questions for you guys. And so there are gonna be questions throughout. You're gonna answer them. Hopefully we're gonna get through this and it's gonna be fun. If not, it's gonna be awkward for me and I'm gonna be sad. So the first question that we'll start with is this one. Does anyone know what this is?
8.
It's this week.
It's 8 this week.
All right, we're here in 8. 8 it is, excellent. Good work, team. All right, so second question.
42.
42, excellent. I wasn't sure how it was gonna play, and it played a lot better than I was expecting. So good crowd, we're among the right people. So if you don't know, it's an in-joke about from his Hitchhiker's Guide to the Galaxy by Douglas Adams. You should go read it before your next seminar. I think that would be appropriate homework. So what are we going to talk about today? This is not for you guys. Unless you want to get up here and give the talk, I welcome it. I will answer that and say, you know, there's going to be 3 big things that we're going to break this presentation up into, and hopefully it's going to be not like pulling nails, but sort of fun. So the first bit's going to be some overview of how I view machine learning and medicine, how they sort of interact. And this is just like grounding stuff, fairly general. I was able to watch Dr. McCarr's presentation, so I don't think we're covering the same stuff as her. I wasn't able to watch Dr. Welge, so I don't know if we're going over the same stuff. You guys will let me know and we'll just move ahead, right? The second portion is probably the majority of what we'll talk about, which is going to be focused on building a machine learning model for occupational injuries. And so we'll talk about like the development process and some of the things that came out through my work. And this is work with Brian primarily. And then we'll finally talk about the paper that you guys read. And this is sort of on the end, tail end of making models, but looking at evaluation of models. So let's jump into sort of my view of machine learning and medicine. And so just as a note, it's a little biased because I have the world of machine learning and medicine up on the screen. There's 3 things, and it's the patient, it's the physician, and the prediction. And the reason why I have these 3 things is because they're all P's and the alliteration is great. But it's sort of, it's a little facetious. Physician is just really because of my own bias. That's why I put that there. And it's throughout the rest of the slides. but really anytime you see the blue position, think about this as clinicians, anyone on the healthcare team, anyone that's not even necessarily directly taking care of patients, but people that are sort of administrative or higher level folks that are thinking about patients or populations and using machine learning methods or other various statistical techniques to apply predictions and then make decisions based off of those on specific patients or groups of patients or populations. So we'll be focusing primarily on how we make predictions and how do we make things that make predictions. So how do we make predictions? This is first real question for you guys. What are your thoughts? How would you make a prediction? If I asked you to make a prediction for me.
Toss a coin.
Toss a coin. So we're making a binary decision here. We're going to toss a coin. This is how I choose restaurants. Me and my wife, like, we'll both pick a restaurant and then we'll toss a coin. And that's how we pick one. So that's, you know, it's 100% accuracy at the end if we go with the choice of the coin, right? What other techniques are there to make, yeah?
Analyze some historical data, look for patterns and use that to make the predictions.
So you can go look at a bunch of data, right? And then you can say, based on this data, you know, most of the time we're going to see this or that, right? And so using large amounts of data, and maybe you're building a model, right? Any other thoughts before we go further? I like the coin and I also like the data. I think both are appropriate for different scenarios. So you can also use a crystal ball. I don't have one. I don't know of anyone that has a good one. But primarily what I work on and what many of you may be exposed to are data-driven models, right? And so what is a data-driven model? Well, there's three sort of components to it, right? There's the input, and this is what we know. And in healthcare, this can be things like age, heart rate, comorbidities, medications. We're going to pass this information to a model. And this can be, it could be a coin flip, right? It could be something more complicated. It could be just a series of rules. And then that model is going to give us something back. It's going to give us an output. And this is something that we like predicted that we don't have access to today. And so this can be something like, you know, your future risk of diabetes or expected risk of diabetes, expected length of stay for a patient in the hospital, any number of things, right? So this is just sort of a general view of input, model, output. And you've seen this in probably many of your different classes, right? You can have many different models. Mathematically, can be expressed very simply, right? With an input, we'll call it X. We'll have a function, which will take the X, and then it'll give back a prediction. And we'll put a hat on the Y because this is a prediction, it's not the actual ground truth. Pretty straightforward, right? Okay. So how do we make models? How would you go about making a model if I gave you a bunch of data? Has anyone made a model?
Random forest.
Random forest. All right, we got a random forest fan here. Any other? Random forests are great. Anyone else? Maybe this side of the room? How about maybe, have you heard of anything that rhymes with Smarkov chain? Markov chains, right? Like you could fit some type of distribution, things changing, like Markov chains. You could also do like a logistic regression. So there's many different types of models that you can fit to data.
Someone put linear regression in the chat. I just want to acknowledge.
Yes, thank you. Linear regression, great. We got K nearest neighbors also on the chat. We got some great stuff going on in the chat. Thank you, chat. So there's also potentially you might have a lot of knowledge, right? So you don't necessarily need data. You could build a model with knowledge. And in healthcare, we have both data and knowledge. We have a lot of stuff that's been instrumented, right? We have our physicians going and taking care of patients. We have nurses charting vital signs regularly for the patients that are in the hospital. We also have occupational therapists. We have respiratory therapists. We have nurses that have tons and tons of both didactic knowledge, so they've been through many years of schooling, and they also have a lot of experience. So they have this physical experience that they've put into knowledge in their own minds, and they have a mental model of how things work. So you could take both of these things and build different types of models from that. So on the left, your guys' left, and my left on the screen, you could take data and you could fit a line, right, a best fit line. Or you could take some type of understanding of the world and you could build, you know, an algorithm, right? You say, if it's this and then that, right? Like this is just taking expert knowledge and building building sort of a formal explanation of how these things are related. In both cases, you want to make sure that you're fitting the need that you are sort of trying to tackle, the prediction. You're trying to make good predictions. And oftentimes in the data-driven modeling approach, what you're trying to do is optimize something. You have a loss function, right? And that loss function tells you how well your function is working on the data that you have to evaluate. And it can be something like this, which is just mean squared error. I'm sure many of you have seen this, but it says how well is this model making predictions compared to the ground truth. And we want to minimize this. So you'll use some type of solver. I'm sure many of you are familiar with solving some type of minimization or optimization problem. And we have experts in the room that do this. So how do we implement a model? Has anyone taken a model and used it in real life? I'm sure some people have done either in internships or consulting projects for classes, have taken a model and tried to use it. Any thoughts? How do you do this?
Could feed the data, feed the model the data that you have, and then see what the output is.
Yeah, so you can take data from like a workflow, right, and connect it. And then you could use that to make decisions. So that's basically it, like wire things up. But the real answer is you have to do it very carefully, right? And not to say that your answer isn't right, it is right, but I also view this as 3 easy steps, just like the model being 3 easy steps. You will develop a model, right? And oftentimes this is taking large amounts of retrospective data. So this is a little database that I have here. And then you'll fit a model, so you'll get your f of x, right? And then you will evaluate. You're gonna say, hey, does this work well for what I'm trying to do? And then if you say, oh yeah, this works pretty well for what I'm trying to do, then you'll go and implement. And I have a little emoji shushing face right there. And this is because in healthcare, oftentimes we want to silently implement something. So we want to go and use it, but we don't want anyone to know about the things that are being predicted, right? Because you can impact the actual workflows if you start to give information or adjust the workflow, right? So you might want to say, well, how well is this going to work in real life, but without actually implementing it into the workflow? This is implement sort of what we call prospective silent implementation. And so you'll take the prospective data, your infrastructure, you'll connect prospective data. So this is like real-time data that's coming from maybe an electronic health record or various other system, and then connect it to your model, and this will give you your predictions. And then you might think, well, we can go on to the next step. We can have users use it. Well, no, stop, evaluate. Every single step, you're gonna see what the pattern is emerging, I'm sure, really quickly. Because these are actually different things. This retrospective data and this prospective data, although they may be coming from the same system, they might be coming from the same electronic health record, they actually look slightly differently. And this is sort of an aside, but we had a small study that I did with Dr. Wiens, where we actually looked, if you have a model that you built with retrospective data, and this is retrospective data from an electronic health record, and then you take that model and you go use it prospectively with the same electronic health record, it actually, you get some performance degradation. Your predictions are not as good as you would expect because there's differences in how data come in over time. And over time, data will actually age and get sort of curated or get better in these like large retrospective databases. So you might not expect to see the performance that you might be getting when you use something prospectively. So that's just a word of caution. So you should evaluate. But let's say it passes the evaluation. You can go ahead and use it. But really what you should be doing is monitoring it. And what is monitoring? It's just evaluation, right? So remember, last slide of the section, to A, B, C, D, E, right? Always be doing careful evaluation. So if you don't take anything else from this talk, this is the one slide. So any questions on that overview? I know that's like very, very high level, very 50,000 feet. I'll take a moment for you to the room if there's anything that comes in on chat. Otherwise, we'll transition into the next section.
Can I just share a story?
Yes.
This?
Yes.
So we made a model to
I'm gonna turn
project.
my back to drink, but I'm listening.
We made a model based on Michigan medicine data to predict what patients would fail physical therapy and go on to surgery for rotator cuff tears.
Mhm.
Used the support vector machine model. We did k-fold cross validation
Perfect.
and and a whole, hold back to set for evaluation
Yep.
versus training. We did all of that.
Yep.
We got this fantastic model that had 98% prediction accuracy.
Ooh, okay.
So then we sent a med student over to Beaumont to collect a bunch of data from over there.
Yep.
Applied the model, total garbage, okay?
Why?
It was unclear,
Okay.
but there's something different about that
Yeah.
context and this context, okay?
Yeah.
And this, my point, is the cautionary tale about evaluation.
Yes.
About transportability to
Yes.
other places.
Yes.
Rather than just at your place and assuming that it'll transport someplace
Yes.
else. And that's a lesson that I learned.
That's actually, so there's a really nice New England Journal perspective piece that sort of talks to that point. Because a lot of times people say, I have this new model, and then they're like, oh, let's go use it at Beaumont, right? And then don't have good performance. And what do you do about that? Like, what does it mean, right? Like, can you be okay with that level of performance degradation? Maybe it might be useful. Other times it's totally garbage. So I think I don't really talk about this at all in this talk, but that's another type of data set shift or transferability that's like massive, massive, massive that you should be thinking about. Any other thoughts or questions? That's just a phenomenal story. What did you guys do?
I decided, what I learned from it was it's so easy to overtrain with sophisticated, machine learning models. I decided to not pursue machine learning because I do something else with my life.
Yes.
That didn't have those kinds of pitfalls.
And that is the ultimate answer.
That's a pretty good answer. And slowly over the course of the dissertation, I'm starting to get, I feel like not quite there yet, but maybe, but that's like when I leave, that's like the takeaway from the thesis. So no, I do believe in machine learning, but I think that there's a lot of hype and there's a lot of stuff that you need to really cut through carefully. And so let's talk about building a model and sort of the steps that we've taken thus far on that model. And so this is looking at building a model for occupational injuries. And I'll talk specifically about occupational injuries in a moment, but I first want to frame just the thinking about this project with a bigger step back. So if you think about, if you've been to the doc and then you've been explaining to them some of your symptoms, you might say something like, hey, I've had this cough for a couple of weeks, right? Or, I was on this med, but I'm not on it anymore. And then, blah, blah, blah happened. Or you might say, I had this surgery like 2 months ago and then XYZ happened. And can you tell me what's going on? And then the physician might respond with questions like, well, oh, that's interesting. Like, tell me what happened afterwards and then what happened, right? So they might ask for the story, or they might say, well, what meds are you currently on? Or they might, if you're managing a chronic disease, they might say, well, how good is your like blood pressure control in general over time, right? So they might ask, a sense of trajectories or trends, right? So there's this notion of time, and time is super important when you think about medicine, right? Because we're people and we exist over time and our diseases change over time. And so the model of models that I introduced to you guys has no notion of time, right? It's just input through model is equal to output. So the general idea in this work is like, well, shouldn't our models also have a notion of time, right? And how could we go about doing that? Anyone have an idea of how we could modify this equation so that we have time in there? Maybe someone.
Creation stuff, updating every times.
Yeah, so you could update over time. So how would we do that? And like maybe how would we modify our equation, right? We could put time on there, right? We could say we're going to have an input that changes over time. So it'll just give me the input at day 1, right? And then I'll give you the prediction for day 1. And then you can just do that over and over again, right? So you can do some type of updating, very on face level, very simple, and actually not like incredibly complicated on a deep level, but we'll get like, once we get into sort of the method that we have, it's a little bit more complicated than this. And throughout the remainder of this section, I suppress, there's not just the notion of time, there's also the individual, right? So you should be indexing your inputs by different individuals if you're doing stuff in healthcare usually. So that's usually it's like suppressed in most of my notation. If you're interested in like pre-notation, I would recommend looking at our hopefully forthcoming paper in JAMIA. But most of the notation has like been suppressed for presentation purposes. So this is dynamic, right? We've indexed over time, perfect. Now let's turn our attention back to occupational injuries. So occupational injuries are relatively big deal. Prior to the pandemic, I don't know if these stats still hold during the pandemic, but 3 out of every 100 workers in the United States will experience an occupational injury on the job per year, right? So this means that a lot of people are getting hurt, and this can be various things. It can be like a crush injury from a forklift, where you crush your hand, or it could be like a lumbar sprain when you pick up a box, right, and you throw out your back. These have a variety of impacts on the different patients, right? It can be you leave work for the rest of the day, or it could be months of disability. And if you look at the workers' comp claims alone, right, just these are like insurance claims essentially, in terms of costs incurred to insurers or workplaces, it's on the order of like $60 billion per year. And when you look at the total economic cost, this is in the hundreds of billions of dollars. When you incorporate lost wages and productivity, it's a big deal from both a personal level and also a sort of societal level in the United States. So the existing models that sort of exist for occupational injuries are often bundled up as sort of, they're sold by people that do guidelines, and medical guidelines are phenomenal, right? Like as a physician or physician trainee, you often use guidelines and you're like, oh, I can expect this person to have this type of recovery, and then, we should use these things to treat them. And so there's this guideline, a couple guideline companies that make models, and they make models by looking at specific types of injuries, and they build essentially logistic regression models for these specific types of injuries. And then they have some expert input where they'll like modify the predictions based on what these experts know. And they're oftentimes built on various different types of data. So they'll have lumbar sprains built with one type of data, and they'll have different type of injuries with a different type of data. And then they're also often built as static prediction models. So they are initially designed to be used at the time of injury, and then you get a prediction, this person's gonna be back at work in 50 days. And then you can't really use them again, because after 10 days, maybe they've had some cortisone treatments and they've done various other things and they're recovering in a certain way, but you can't use that with the static models. The models have already evaluated and you're sort of left with the original prediction. And you need to sort of, as a decision maker, use your best judgment to modify the prediction. It's not built into the model. So our goal for occupational injuries is to predict the work status. That is, if a person is going to be at work or not at work in the future over the course of a patient's recovery. So this is from the very first date of injury until the end of their workers' comp claim. And we're limited in our problem structure because of the claims data that we have. And so there's all kinds of assumptions that we make that are not necessarily great assumptions for a model to be used in the real world, but that's sort of the setup that we have given the data that we have. And so this data set was courtesy of Pierce Health, which was our partner. They're based in Chicago, and it had about 1.2 million injured patients in this claims data set. It has demographics, so this is the age, sex, job. It had a bunch of observations, so this is diagnoses, procedures, and then the return to work dates for these patients. And patients might actually return to work. They might be at work for a couple of days, and then they might not be fully recovered or not able to do their daily tasks, and then they will leave work again. So there's some patients go and come back from work, at least in the data set that we've observed. And so you might say, well, what does this data look like? Well, let's say we have a fellow Wisconsinite. They're a 25-year-old male dairy farmer, right? And they got injured in the milking parlor. And over the course of time, some information is collected in the form of diagnoses, procedures, prescriptions, and then we also collect their work status. So we know if they're working or not. This is a contrived example. It's not any data from the actual data set. It's just something I made up. So that the idea is that we would be observing this, and on day 7, we would see, hey, they got an MRI. And then if we were like omniscient, we could look into the future and know, hey, tomorrow they're not going to be at work. And then we'd also have this back catalog of information that we've been collecting. So the key idea is to make the dynamic prediction like a physician would, right? Can we think about this problem like a physician would, and then map that into a model so that maybe someone like a physician or insurer that's looking at these people over time might be able to use predictions from this model. So what would, a question for you guys, and it's not on the slide, so I apologize, but what do you think a physician would be thinking about presented, let's say our farmer's name was John Smith, presented about like John Smith, what do you think a physician would ask themselves, or what would they think about? Yep.
And maybe what's medicine to do take after that. And then the physician maybe generate some of the possible,
So they would say, okay, what happened previously, right? And then where are you going, right? So are you gonna be at work in a day, right? So prognosis potentially. Any other question? Yeah.
How cynical can we be here?
You can be as cynical as you want.
What can I bill for?
What can you bill for? This is a great question because we're not going to talk enough about this in this talk, but what can you bill for is entirely what this data set is about.
Yeah, it's back sprain.
Yeah,
Okay, if you see a neurosurgeon or orthopedic surgeon, that's a very different thing
exactly.
than a PM&R.
Exactly. So this gets to like a subtle point in bias that I'm going to bring up at the very end of the presentation, but you have to think about this type of thing because this is actually the underlying data generating process, is that not every patient is going to go see, you know, the average physician. They're going to go see a bunch of different physicians, and the physicians have different practice patterns that are incentivized differently, right? Some might be at your Mayos of the world, where Mayo, you know, allegedly doesn't have as much like fee for service, right? So thinking about other parts of health system, you know, health systems engineering that you guys know about or have been exposed to, that impacts the data that we see, right? So if we got this data from the Mayo Clinic, might be very different from the data set that we have. So, you know, cynical, but important, right? So what kind of physician is this? How are they practicing? That's not a question that I have on my slides, but, you know, I have the prognosis question. Will this person be working in a day or X number of days? And then also to your point, what do I currently know about the patient? So what has happened to this patient? And then what has happened to this patient, right? So these are the three big things that I was thinking about. But the cynical question is an important question to think about and to have in at least the back of your mind, and maybe be something that you're designing for. So let's map this like physician thought process onto some notation. And again, the note about the notation, these shouldn't be capitals, but I refer you to the hopefully forthcoming paper from Jamia that's under review. So we're gonna have this current observation is X of T, so that's what we've observed today. And then what we're gonna try to predict is Y of T. And so let's say we're trying to predict a day in the future. So Y of 5, so we'll index by time, Y of 5 would be working tomorrow. So we'll call that a 1 for this project. And then what about the history? Well, the history is all of this stuff, right? So on day 5, they have a history of 0, 1, 2, 3, 4 days of history. And we want to have a model that has all of this because it sort of maps to physician thinking. So what are some desired attributes? Can anyone maybe throw some, like if I were to tell you I want a model that has these types of things, how would this model behave? You guys have any ideas? That's all right, I have some ideas. So we're gonna use some observations. We'll use observations and history for the predictions. We're gonna use both the observations, the daily information, and then also the history to make a prediction. And then the history should be an accumulation of all the observations. So as I watch daily, I should be building this history over time. I'm just gonna look at the chat real quick. So to be clear, we are interested in when a person will return to work or when a person can return to work. Michael, this is a great question, a subtle difference. So we're interested in when they will return according to the claims data, not necessarily when they are fit to work by determination of a physician, not when they should be at work, right? This is, again, our setup dictates what we're trying to do. So all your assumptions that you're making, again, a subtle point about machine learning, this is key to how you frame your problem and how you evaluate it is actually what you are learning, right? It's not going to be anything other than that. Just like your optimization, like when your objective function is a certain thing, you're not going to get something else when you set that objective function. So how do we encode these like desired attributes? Well, for this this first line, we could say we'll have a function. Let's call this f of y. That's going to take the current observation from today, and then we'll take the history up until today, and then we'll give you a prediction for today, because that satisfies sort of our attributes there. And then for the bottom sort of attribute, we'll take we'll call this another function. And these, you don't have to worry about the H's or Y's on the function, they're gonna go away soon. You'll take the current observation for today, you'll take the history up until today, and then you'll create a new history that includes today, right? So this is relatively simple, but these are sort of attributes that we want our model to have. And so you could say, well, let's just have one function that does this. And there you go. You have one function, your f of x t takes h of t minus 1, so the history up until today, and then you'll get a prediction for today y, and then you'll have a your updated history. So you might notice that there's h's on both sides of the equation. So this is recursive, and you need to figure out a way to recurse the history over time. And you can have sort of a block diagram where you show this, and we won't go into this in particular details because I don't think we need to like belabor this point. But you can see, if you have an h of t from the previous day, you might want to pass it forward to the next day. And so you'll have over time, you'll have inputs coming in, you'll have a previous history, day's history, and let's assume that you can start with some good history. And you'll just sort of pass it forward. For every single day you have an observation, you'll store this history, you'll get a new observation, you'll make a prediction, you'll also make a new history, and then you can do this day over day. Does that sort of make sense? It's sort of trying to map to what physicians are doing. There's no guarantee that it's picking up on what we would like, because it's just sort of, this is the structure that we're choosing. We're going to do this in a neural network. We have no guarantee that it's going to actually learn what we want, but that's sort of the structure that we decided to go with. There's a couple little subtleties in this, and I'm going to sort of go through these quickly because I think the next set of slides in the third section are more important for us to discuss together. So we'll just fly through these. But if you have questions, ask me and we can go through them offline, or we can talk about them on email. So a lot of these data actually can't be used directly. And the reason for this is, if you think about your X's and your histories, your daily observations, I have two different types of observations here. I have lumbar sprain for diagnoses. I also have major depressive disease or disorder for diagnoses. But there's actually, if you look at the International Classification of Diseases, there's over 10,000 different distinct diagnoses. And then if you look at procedures, if you look at the CPT codes, which are the, I think, current procedural terminology code set, there's like 50,000 different procedures. And you can have very like high cardinality observations that you put into neural networks. But this is 10,000, this is 50,000, and this is like potentially, depending on how you have your prescriptions encoded with like their, if you have Tylenol 50 milligrams versus Tylenol 100 milligrams, right? Like all that stuff is like it becomes combinatorial explosive. So this is like potentially in the hundreds of thousands. And so if you wanted to have one vector that described all that stuff, it could be massive. It could be like, could be hundreds of thousands of elements long. And that's not great from a computational standpoint. It's not great from a memory standpoint on your computer, right? You have finite memory. So what we're going to end, and an additional complication, is you can have more than one diagnosis on a day. You can have more than one prescription. You can have more than one procedure on a day. So we're going to make some assumptions, and we're going to try to simplify this information that's coming into the model, just so it's a little bit more computationally tractable. And so what we do is we put tildes on these things. And the tildes, what they do is, one, we restrict the number of diagnoses that can be observed on a day. This is like a user fixable parameter, but we have generally, I think it's like, we have what we call 5 channels. So you can do up to 5 diagnoses per day, up to 5 of each of these categories per day, randomly chosen. And then we represent each of these distinct categories as a vector. It's a low dimensional vector of maybe size like 5 or 6. And then we say that the model can learn what these things should be, like what the lumbar sprain vector should be. And this is a technique called word embeddings that's borrowed from natural language processing, but essentially allows the machine learning model to say like, well, how do I represent this thing in an efficient way and make things that should be different, and make things that should be similar. So the general architecture is that now we have tildes on these things, and the history, of course, is the accumulation of all these inputs, right? So that especially needs to be condensed down, so that's why it has a tilde. And then if you look at what's under the hood for, this is like a neural network. We have 3 big components. The first one is the actual data that comes in. So this is inputs at time step t, has the age, the sex, the job, diagnoses, meds, etc. It's transformed by TensorFlow, for those of you interested in knowing about our implementation. And then it goes into an ingestion layer. This is going to create sort of a more parsimonious version of the input. So it squishes the input down even further so that we can be more efficient with our math and our computation. And then we get a double tilde x, which is just it's like essentially you can think about it as an encoded input. It's doubly encoded input. And then finally, sort of the meat of the sandwich, which is this information or the observation comes into the middle. And this is where we interact with the history. So we'll take yesterday's history and then we will update it with the observation that we had today. We'll store it in the history, which we'll call this like, it's a vector. So it's like the health state vector or the history vector. And then we can use yesterday's history with the observation to make a prediction. So there's a final little bit that does the actual prediction making. And then we get our y hat of t. And one of the nice things about this like architecture is we can actually, because of the thing, this history is not a specific history. It's not like a return to work specific thing. It's a history of all the observations. We can make different types of predictions off of it. So you could make a prediction about like, oh, they're going to need an MRI in 3 days, in addition to knowing that they're going to be returning to work in 3 days. We don't do that in this work, but it just sort of allows us for that extension in the future. So how does it work? Here's an example of it working. And this is a male truck driver, approximately 40 years old. And on the y-axis, it's predicting the work at probability of this person being at work tomorrow. And this is actually a prototype. I made this video a long time ago, so it's not the actual like final model, but you can see the probability is initially sort of a little less than 40%. And then after some time, it goes up. Well, this case, like around this time there's a bunch of office visits. And then the cadence of office visits slows down and the probability climbs. And this black line is actually when they return to work. We don't actually include this information in the model. So on face validity, right, you just want to know that the stuff after this line, is that closer to 1 than the stuff before the line? And it's sort of, for this prototype version, you sort of say, looks like it's doing roughly the right thing, but the timing of it might not be quite right. And what I would say to that is this model is not meant to be used for individual people. It's meant to manage populations. And there's a whole bunch of evaluation that needs to be done before we go anywhere with this model. But this is just sort of an example. So we get daily information, the observations, and we're going to make predictions every day. And then you might ask, well, how well does it work? So in terms of some experimental setup, we compare this to an optimistic baseline. So the optimistic baseline essentially tries to recreate what's going on in industry, which is a static prediction. But it's tricky because it's a static prediction, but we don't want to handicap the model because it's unfair to have one really complicated model that can learn a lot of stuff from the data and then have one model that's not very complicated and can't learn a lot of stuff from the data. So we essentially try to make a model that's at parity, but we limit the way the information is passed to it. Hopefully reviewers are going to like that justification. It's not great because we don't have access to the existing baselines because they're proprietary. So this is a limitation of our work. But we have what we believe is an optimistic baseline. We try to predict if the patient's going to be at work in 7 days. And there's a label, it's either 0 if they're not at work and 1 if they are at work. And then we split the data set into training, validation, and testing with 100,000 each. We actually have 70,000 leftover patients just because of computational issues. We didn't want this thing to run for months. So we cut the number of patients that we're using, but each of these sets is independent. So the patients that are in the training set are not in the validation or the test sets. And the objective function that we're actually trying to minimize here is the binary cross entropy loss between the predicted labels and labels. And this is essentially just trying to make the predictions be as close to, if it's actually a 0, as close to 0 as possible by the model. And if it is a 1, as close to 1 as possible. But what it produces are values between 0 and 1. And they can be interpreted as probabilities because they're real values between 0 and 1. And the way that we evaluate this is we're going to take all the daily predictions for each patient, and we'll look at all of those predictions And then we will see how well they do in terms of discrimination. So this is being able to split the people that return to work from not returning to work. And this is actually patient days. So that's splitting the two different types of patient days if they return to work or not. And that we do that with the area under the ROC curve. And then we also look at calibration, which is a measure of how well the estimated risk from the model matches observed risk. So some results, really briefly, we have our discriminative performance here. Our model is statistically better than the baseline. And it's sort of in the good, fair range with 0.73-ish is like, decent-ish area under the ROC curve. It's not 0.8, which is usually sort of the slam dunk, let's go like implement this thing, range. But it outperforms the baseline, which is at, around 0.6, which is sort of in the poor range. And really what we're trying to show here is that just moving to this like dynamic system is beneficial compared to using the static baseline. And then in terms of calibration, we have slightly better calibration than the baseline. So that's this project at sort of a high level. I can stop and take some questions. And then Amy, I know that the last 15 minutes is for questions, but I'm hoping the last section is a little bit more interactive. So we're okay?
Do you?
Okay. Any questions before we truck on into the next section? Yes.
Yeah, so I'll just say, when I got my PhD here from this department in the early 90s,
Yeah.
I went to work for a workers' comp agency.
Yeah.
Basically. And I did some modeling of this kind of stuff with neural networks.
Yeah.
So the actual rule of thumb in the claims manager was, if a back pain patient had seen a lawyer and an orthopedic surgeon, they will never go back to work.
Yeah.
Okay.
Yeah.
Now, but we don't know the causality.
Mhm.
It could be that those patients were more severely injured,
Yes.
more likely to see the orthopedic surgeon, go on a
Exactly.
legal route. Or it could be that the lawyer and the surgeon have financial interests
Yes.
in making sure they never go back to work.
Yeah.
Okay. So you haven't talked about causality
Yes.
here. And
No.
and the thing is that, think about it, as you as a future clinician, one thing you might like to do is do things that affect
Yes.
the time to return to work. What are your thoughts about causal modeling and machine learning?
Yeah. So I think I was actually having a conversation with someone in Jenna's group that does causal inference work. And one of the things that I actually asked him, I was like, what is the general physician sentiment on causal inference? Because, he's the one that's interacting with the physicians about it because that's his research work. And he's like, like a lot of them don't even really get it, right? And some of the causal frameworks are actually like, I don't know if anyone has seen that stuff, but it can be a little bit complicated because causality is complicated, right? You try to say, with the data that you have, which is usually observational data, if I know Y, right, and I also know X, but there might be a confounder, let's call it a treatment T, how do I know that that interaction between X and Y is like due to the treatment and it's not due to something that I'm not observing, right, an unobserved confounder. And I think, right, like, so putting the clinician hat on, like, randomized control trial is like, that's why we do these things, right? Like, you can go and do a randomized control trial, you can really effectively determine what is a cause and what isn't a cause. But a lot of times in real life, we can't, it's not like, it's either not ethical or it's not practical, or like, with the lawyer example, like we can design an RCT where we randomly assign people to a lawyer and not, and then like see what happens, right? You could try to build the study that would do it, but I think what you need to turn to is some of the causal inference literature and techniques there and see, what is the association here? Can it be teased apart? Can it not be teased apart? And there's all causal inference, like there's a reason why I'm not like working on causal inference, because it's like, it's hard, right? And I think it's necessary to untangle some of that stuff. It's just, right now, this is entirely looking at correlations. We're not interested in causal.
Can I make one more comment?
Yeah.
So your initial PPP diagram left off two other P's that relate to the occupational injury.
Yes.
Which is payers and politicians.
Yes.
Okay.
Yes.
And the financial incentives for return to work are regulated at the state level, not the federal level.
Yep.
Right? And periodically states go through and change their laws, they call it reform.
Yep.
That have a lot to do with limiting, you know, things that allow for longer, you know, time away from work. Did you include your model state? If you had a big database,
Yep.
did you include state
So
level factors?
it was all in one state.
Oh,
Yeah.
good, okay.
So we like,
Can I ask
so
what
one,
state?
well, it's in Ohio.
But they have a monopoly state. How, so this,
We got.
so Ohio is one of those states that you have to buy workers' comp insurance from the state
Yeah.
unless you're a self-insured.
Yeah.
So is that the data set
Yeah.
you're working with?
Yeah.
Oh, cool.
Yeah, so one thing that we were interested in doing is we have another data set that's from California, and you could just see how well does this thing work in California, right? And I'm assuming this curve going down, right? Like we're picking up on probably Ohio specific things. And yeah, so excellent points. Anything else before we?
Yeah, I just had a quick question. Could you go back to your model graph for the, where you're going to, yeah.
This one?
Can you explain,
Yeah.
do you know why the model has these dips at like 100, 152?
So there's office visits on these days.
Okay.
Yeah.
I figured it might have to do something.
Yeah, so I went and looked, and I have in my notes, I have exactly what happens on each of these days, and those are, there's also, yeah, there's an office visit on day 97, there's a diagnosis in addition to an office visit, they have a contusion of their ankle, and then they have a traumatic rupture of their, like, so there's like all these like additional diagnoses that like given and everything else, like their background would be sort of a indication of like not returning to work, but this person had clearly returned to work. And we don't include that like work status in the model. Once you do, the model performance like skyrockets, but we didn't want that. We would just wanted to see like what's the effect of like having dynamic predictions in this task. So there's a long way for this model to go before we even consider potentially like a silent implementation or, you know, going into like the real world usage, right? So let's really quickly like talk about the sepsis task, which is the paper that we read. So sepsis is, and it's sort of at this like phase where it was like silently implemented, and then we're doing the evaluation to see, you know, should we use this in actual clinical practice? Sepsis is a big deal, approximately 2 million cases per year. Michael, I will comment on important features if you email me. Let's just keep this train going. So sorry, respond to the chat for you, those of you not looking at the chat. Sepsis, there's about 2 million cases per year, and this leads to about 300,000 deaths. And the issue is that these deaths are often very precipitous. So patient can be in the hospital, they can have an infection, and sepsis is essentially just a disordered response or immune response to an underlying infection. And so someone might be like, okay, and then they might just like tank. And oftentimes you want to respond very quickly and aggressively to someone that you suspect might be experiencing sepsis. So there's a lot of people working on early warning systems for sepsis. Epic, who is a electronic health record vendor, has a Epic sepsis model. And it is sort of highly recommended that you use their Epic sepsis model, or if you don't, you should use one because you get sort of a bonus or like a kickback, not a kickback per se, but you get a reduction in your yearly fees for using Epic. And there's like some problems with that, but that's an aside. And if you're interested, you can email me because there's a whole bunch of stat news articles about this. And it's an interesting space to be working on. So for those of you that read the paper, was anyone able to discern like how does the model work? Like what inputs did it have, what outputs, and then how often does it produce scores for patients? It's all right if you.
Well, it's the chart, right? The hospital chart, which means anytime somebody looks at the patient, something gets updated.
So it's the chart, right? But it's a subset of the chart because the chart has like, could be like notes, it could be it could be, you know, does it include imaging stuff? It doesn't necessarily include that, but it does include, it includes, and this isn't actually even in the main text of the paper, it's in the supplemental. And if you want to know actually what's in this model, you have to go and like get like special access from Epic in order to know like what the specific variables are being used. And we don't know what their weights are. So we don't actually have access to the full model. But it's vital signs, generally speaking, medication orders, lab values, comorbidities, and demographic information. And the outputs are the ICD-9 code which is an indication of a diagnosis of sepsis. And then they like time it such that they like try to see when someone might have had sepsis. So the way they do that is they look to see when antibiotics were administered. And then they say, oh, well, the physician probably knew that there was sepsis before that point. So we'll just roll back the time to 6 hours prior to this. And so some of you are raising eyebrows, and this is eyebrow raising point that we'll get back to. And the implementation, it runs every 15 minutes on every patient in the hospital. And Epic recommended that we set our threshold to about not 0.6. It's the scores run from 6, they run from 1 to 100. They recommended alerting after a score of, or above a score of 6. And I have an example person here with totally made up numbers on the timeline, but you can sort of see alerting above this threshold. And so how would you evaluate this model? Just in the interest of you guys asking me questions, we'll skip through this, but you could sort of handle, there's a lot of scores being produced for this patient, right? Just like the previous model, we're producing many scores. It's a dynamic model. So you could chunk up the encounter into days or something, and you could say, did the prediction for this day and the next day, did that do the right thing or not? And that's sort of like what we're doing in the occupational injury case. Or you could sort of look at this at the whole encounter level and say, over the course of the encounter, did this do the right thing? And in both of these cases, you need to find a way to like aggregate. There's multiple scores being produced. You need to figure out a way to aggregate those scores to compare against the label, and the label being 0, 1. And for the encounter level, we take the maximum score observed, because the idea is that the maximum will always, if there is a threshold, it will always hit the threshold. Or if it doesn't hit the threshold, it never hit the threshold throughout the history. That was a bad explanation. I will gladly take questions on it. But then thinking about like the outcome and integration into workflows. So this was not integrated into workflows, and the outcome we will talk about. So what was the general study setup? Do you guys recall? Where did we do it? Michigan Medicine. And for approximately how long? It was a little less than a year. And then we also did it on who? What population?
18 and
All, yeah, pretty much everyone that was 18 and older, all inpatients, except for a couple units where there were actually alerts firing. So what was the actual outcome that we were trying to evaluate? So there's a sepsis definition, and the sepsis definition is different than the one that Epic used. And this is based on we have a vendor called Health Catalyst, and they actually try to like do a good job of figuring out when people have sepsis. And there's like 2 components to it. And it uses some physiological information to look and see, do you have organ dysfunction? Yes, no, okay, here's the time that we think you actually had sepsis. So it's a different definition, and it's the one that we use for our quality improvement initiatives. So this is, for your eyebrows raised, remember this point's gonna come back. Do you guys remember some like the salient numbers that came out of reading this paper? Anything that like struck you that was like, oh, what was a big takeaway finding in terms of numbers? And I'm gonna just check the chat while you guys are thinking about that.
And I don't remember the actual numbers.
No, that's all right.
There were a lot of cases of sepsis that the Epic model missed.
Yeah. So that's, we'll have in the slide after this one that I'm about to show you here, that'll sort of come to light. But this is sort of the most important figure from this paper is table 2, in my opinion. And the column that's most important is this one. So this looks at a hospitalization level performance of this model. And so this is like over the course of the entire hospitalization, would this model have fired an alert appropriately? So the outcome incidence, so this is the percentage of patients that actually had sepsis, was approximately 7%. And there's about 30,000 patients that actually met the study inclusion criteria. The AUROC was 0.63. So remember, we were talking about the previous AUROCs, and that's sort of in the poor range. And compared to what we were told by the vendor, where it was going to be, we were expecting it to be 0.8, that's a big drop, right? So that's a big difference. And you can also think about this AUC. It's also the probability of if you're given a patient that is septic and not septic, the probability that the model correctly ranks those two people. So, you know, you can think about like, well, you're just a little bit above random here. And then if you set a threshold of 6, what is your positive predictive value? We'll walk through these numbers in the next slide or so, but it's 12%. So who here has seen confusion matrices before? Some people, yeah. So confusion matrices are phenomenal, but they're really, it's very simple to like look at a confusion matrix, and once you're like familiar with them, they're really nice tools because on the columns you have the actual conditions. So they actually had sepsis or they didn't have sepsis, and then you're taking the population and you're breaking them up. So we had 38,000 people total, about 2,000 some had sepsis. And then on the rows, you have the model performance. So you have, did the model, was it going to alert? So greater than 6 or not alert? And so you can see, you know, for the 2,000 some patients, about 800 it would have fired for. And that actually measure right there is the sensitivity of the model. So there's various measures, sensitivity, specificity, which we don't have time to get into because we're already way past the time I was going to end. But the positive predictive value, which is oftentimes sort of the utility of an alert, right? So this is given an alert, the probability that the alert is actually firing on someone that's actually septic, to calculate that that's true positives over the total number of people that the model said was positive. So that's true positives and false positives. That's 800 over 6,791. So it's approximately 12%. So you're going to be getting an alert, and there's a 12% chance that the person was actually septic, which could be good. I mean, it depends on sort of your regime and sort of how well the physicians are doing at this already, right? So it might be beneficial, but you have to think about these things very carefully. And one additional thing to think about, sort of the inverse of the PPV, which is the number of people needed to evaluate before you find a person that's actually septic. And so this is literally the inverse of PPV. It's just the number of people that you evaluated, that the model said to evaluate, so 6,791. And then there are 800 some people that were actually septic. So it's around 8 people. And that could totally be worth it if it's something that's very serious like sepsis, and it doesn't take a lot of time or effort to evaluate. And you had a hard time finding them previously. A little bit of a wrinkle is like if physicians are actually not terrible at finding sepsis. And so if you go and break the population out by the septic people that the physician found versus the septic people that the physician didn't find, which is this column here, is we're looking entirely at only people that were septic. So this is sort of the left column from the previous confusion matrix, but split based on the physicians did not order antibiotics or they did order antibiotics. So this is presuming that the physician knew that there was sepsis. You ideally would be finding, the model would be finding people that the physician can't find, right? And we're not in, the majority are not here, right? So that's not maybe amazing. And you can sort of calculate like the probability of getting an alert that's useful given it being correct. And I won't walk through that, but it's sort of like, we can talk about it if you're interested after the fact. So that's where we were for that project. So maybe as we wrap up, we'll talk about these things, but you can think about, would you recommend using this model? Why is there such a big difference? It's because there's a subtle difference in the outcome definition. And this is borne out when you do a sensitivity analysis and you include scores beyond when we think the patient is septic. If you go beyond that point by 3 hours, the performance jumps up to 0.8. So I think we have a difference in sepsis outcome timing, and this leads to a difference in performance. And there's always more evaluation to be done. So this group at Metro Health did a sort of a randomized control trial using the EPIC sepsis model. And I can share this with people that are interested. And they saw small but meaningful and significant improvements in time to antibiotics in the emergency department for using this model compared to not using the model. So there's some benefit to having the information. So more evaluation is always better. And wrapping up, so we talked about dynamic models. Always be carefully doing evaluation. Good performance is necessary, but not sufficient. There's bias, right? So your model might be doing well, but it might be not doing well on certain minority populations. And you want to be careful that you're not enforcing bias that's in data and continuing to propagate it. And there's a whole bunch of work that's being done on this, and it should be done very carefully. Not going to do sufficient justice to it in the remaining 30 seconds left. There's issues of explainability. Should you be passing information about how the model works back to physicians or other users? And then the infrastructure is non-trivial. Integrating this stuff is difficult. And you can spend a lot of time and effort and money getting this stuff connected. So things for you, I know you, at least when I took this course, you had to reflect on the reading and the talk. So you could potentially think about, if I gave you a new model, how would you think about evaluating it? If you were to evaluate the model that we're making for occupational injuries, what could you take from the study that you read, like maybe design evaluation for that? Yeah, so last point I'd like to sort of underscore for you guys, go back to the Venn diagram. So who has a big role to play in all this? And think outside the circles, people. Any ideas?
You.
Not me, not me, guys, not me, but sort of me. It's sort of in the name of the, it's like the course number, could give a hint.
That work.
Industrial engineers, right? Like you think about all the tools that industrial engineers have, right? Like understanding workflow, optimization, right?